Assalamu alaikum. Welcome to lecture 24 of natural language processing. So today we will continue our discussion on recurrent networks as well as our discussion on deep neural networks in general. When we stopped last time, we were talking about some considerations and you can say issues while implementing deep neural networks. And we had talked about things like the vanishing gradient problem, the exploding values problem. We also talked about parameters and hyperparameters. So we'll start with this and talk about some other issues, primarily overfitting and how to handle overfitting in a deep neural network. And then after that, we will talk about attention-based networks, and primarily we'll talk about the transformer. So the transformer is a much more recent development in NLP and deep neural network. And we will be discussing the transformer as well today. So that is basically the agenda for today. So are there any questions?
अस्सलाम वालेकुम सर।
जी,
मुझे बस
वालेकुम
एक
सलाम।
अगले हफ्ते हमारे क्विज होगा ना एक,
जी जी,
and then
मंडे
we'll
को
be left
इंशाल्लाह। जी
and then we're left with 2 quizzes.
जी। So
तो
that would be
कल
the 9th quiz and we'll be dropping 2. So the minimum 2 grades would be dropped in your final grade.
ठीक है, and the quiz for next week, is that going to include only this week's 2 lectures या फिर पिछले हफ्ते वाले भी, because इस हफ्ते नहीं हुआ था quiz?
हाँ, तो एक्चुअली टिपिकली वो पिछले क्विज से आगे ही होगा, so it will include 2 weeks of lectures.
Okay, ठीक है, thank you sir.
Anything else? So let's start with our discussion on deep neural networks and some of the issues that surround it. So we talked about parameters. So there are a lot of parameters in a typical deep neural network, including recurrent models. And those parameters are basically your Ws, which are matrices, and your bias vectors B. And of course, if you talk about a recurrent network like GRU, Ws would be WA, WY, WU, WO, WF. So all of these would be Ws that are used. And if you have a deep feed-forward network, of course, for each layer, you will have a different W. So these parameters are learned through the optimization process, which is iterative in general. And in the optimization process, we typically try to minimize a loss function. Okay, so loss function is basically a function that quantifies the error that the model is making given our label data. And this minimization is done, as I said, iteratively using stochastic descent. This is a technique for iterative optimization. And of course, there are some variations and there are a number of variations of this basic approach that are implemented in various APIs available out there for deep learning. So let me mention the process of training. So usually what we have is we have some label data is available to us for learning any deep neural network or recurrent neural network. And we divide this label data usually into a training set, a validation set, and a test set. So usually the percentages could be, for example, 70, 10, and 20. All right. And we train the network. When we say we train the network, we are learning the parameters, Ws and Bs. by minimizing the loss function. We train on the training set. But again, to kind of speed up the process, we do not update the parameters after seeing each example in the training set. We train them after seeing a number of examples. That number of examples is usually called a batch. And as such, we say that we are doing batch processing. So basically, process a fixed number of examples so process a fixed number. For example, you can say you're processing 100 examples. What this means is you will feed forward 100 examples. You will aggregate the losses of all those 15 examples and then apply the stochastic gradient descent and update the parameters after those 100 examples. So this is called the batch processing mode, and this is primarily done to speed up the processing. Of course, if you update after seeing each iteration, it might take even longer to train such deep networks with lots of parameters. Okay? So, and of course, the whole data set, which is a training set, may be divided into multiple batches. So processing one entire training set is called a epoch. Okay? So let's say you have, just for example's sake, you have 100 examples in the training set. 10 is the mini batch or batch size. So you will be processing 10 examples at once, then the next 10, then the next 10. After you have processed the first 100, after you have processed the 100 examples, you say that you have completed one epoch of training. So one epoch is completed after 100 examples. Okay? But usually a neural network is trained over numerous epochs. So you have to do it multiple times. Okay? So after one epoch, you basically, actually it's done both ways. Maybe after each batch or epoch, or after each batch and, for example, epoch. After epoch, you do actually do this. You basically evaluate on the validation set. Okay? Meaning that the model that has been trained on the training set is also tested on the validation set. So at the end of each epoch or after each batch, you also have values for training. Sorry. So you have two values. You have the training error or loss, and you also have the validation error or loss. So these two values would help you track how your model is learning. So if you plot them, you will get something, a curve like this, usually a curve that is downward trend. So this is epochs. And of course, on this direction, you have loss. And you will have one curve for the training error, and you'll have another curve for the validation error. Usually the validation error curve will be above the training error curve. So let me delete this. So let's say ये मेरा validation है, तो आपका usually, sorry, training है, ये वाला validation होगा. So this one is validation. So validation obviously is a data set that is not seen during training. So in general, its error or loss will be slightly higher. So based on the trends in the validation set, you then decide when to stop your training. So usually when the validation error starts to increase, you stop the training. Or when the error in the validation becomes, or decrease in error in validation becomes less than some threshold, you stop the training. Okay. Also, usually in neural network practice, after the end of each epoch, you also save all the parameters. So that, let's say if you want to stop at some previous number of epochs, you can get those parameters and use that model right away. So after the completion of each epoch, you save the parameters. So save parameters after each epoch. So just to make sure that if you want to return to some previous epoch, you have that model available with you. Plus, as I mentioned last time you have several hyperparameters. So hyperparameters are for network parameters, optimization parameters. They could be regularization parameters, and there could be others as well. So these parameters are optimized or decided over the validation set. So you first run the model multiple times with multiple settings of these hyperparameters and see which set of hyperparameters would give you the least performance over the validation set. Sorry, the best performance, the loss is minimum over the validation set. Once that set of hyperparameters is fixed, then you use them and train it again over the training set. Okay? So this was kind of an overview of the process, and there are some terminologies used here which are kind of more common for neural networks. So I wanted to mention this to you: the idea of batch, the idea of an epoch, the whole issue of hyperparameters, how you decide those hyperparameters, and in general, in most practical neural network practice, you save the parameters after each epoch so that maybe you want to use a network at a previous training level. Okay, now let me talk about layer normalization. So this is another technique that is commonly used in neural networks nowadays. Why we do this? The main reason is to improve convergence. So what is convergence? Your network stabilizes, meaning that its validation error becomes small or doesn't starts increasing in a stable manner as well as in fewer iterations. So that is convergence. So we would like to improve the convergence, mean that we want to get the convergence in smaller number of epochs, as well as maybe the convergence is very well defined or smooth rather than jumpy. So layer normalization is a technique that is commonly employed for this. And sometimes it also helps in preventing overfitting. And we'll talk about overfitting just shortly today. We had already talked about overfitting before, so you know the concept. So there are a number of layer normalization techniques, and let's mention those very briefly. The first one is called batch normalization. So by the way, whenever you see any neural network architecture, they will usually mention that we have a feed-forward layer, we then have a normalization layer, we then had an output layer. Usually normalization layer, you can draw it as a separate layer, but it's generally a processing that is done after the output. But they typically represent it as a separate layer. So that's why this is usually called layered normalization. So normalization, of course, is usually only done for inputs. It is sometimes also done for inputs, which is like your standard normalization in data mining, in machine learning. And it's also done for the outputs of hidden layers, recurrent layer, या feed forward layer, whatever is your hidden layer. Okay? It is not done for the output layer, obviously. Okay? That normalization is dependent on what you are actually trying to do with your neural network. Okay? So batch normalization, as the name suggests, is done after processing a batch of examples. So let's say you have 100 examples as a batch. So once you have processed 100 examples, you will have 100, let's take that you want to normalize a hidden layer. And its output is the vector A, as we had used the notation before. So now you will have basically this vector A for those 100 examples. So in other words, you have basically A1 to A100. And each of those A's, of course, is a vector. Okay? So you can think of this as, let's say A, मैं कहता हूँ सिर्फ 3 outputs हैं. So let's say A, B, and C, and then you will have 100 such values in this column for each of those columns. So let's say मेरे पास ये 0 है, ये 1 है, ये 0 है, फिर मेरे पास 1 है, 1 है, 1 है, और let's say मेरे पास ये -1 है, ये 0 है, और 1 है, and so on. So batch normalization would have 100 of these rows and then apply Z-score normalization on each of those outputs, A, B, and C, each of those cells or units output A, B, C. So after normalizing, your A would then lie actually. So A, B, and C are normalized using Z-score normalization. By the way, Z-score normalization मैंने यहाँ बताई थी इस कोर्स में? I think I did not. So basically, this normalization is based on the mean and the standard deviation. So let's say we want to normalize A. So let's say the mean of A is M and the standard deviation is S. Okay? Of the whole column A over those 100 examples, which is your batch size. Okay? And then any new value of A, let's say a value of 1, let's say, the new value of एक particular value मैं ले लेता हूँ, let's say A prime मैं कह देता हूँ, notation का थोड़ा सा issue हो रहा है, but let's say कोई value मेरे पास original value is 1, let's say. The new value would be 1 minus mean divided by standard deviation. So you're normalizing all the values in a particular column by using the mean of that column and the variance or standard deviation of that column. After the normalization, the values would have 0 mean and unit standard deviation. So that is a property of Z-score normalization or standardization. So this is done after seeing a batch, which in our case is 100 examples. All the values are now normalized, and then this normalized values are now fed to the next layer using whatever parameters that we have at that point in time. If you're doing you have multiple layer normalization. Let's say there were 2 hidden layers. The first hidden layer का process होगा, normalize होगा, then goes to the next hidden layer. Next hidden layer का भी सारा 100 जब process हो जाएगा, वो normalize होगा, then goes to the next hidden layer, and so on. So the normalization ensures that your values do not drift significantly over time, over the entire data set. So it kind of recenters those values back to the zero mean and with a standard deviation. And because of this processing, there is some randomness added to it, and that's why it helps in overfitting also. But it also improves convergence, because if your value drifts to one side, maybe convergence would typically become difficult, and you won't be able to reach a state where the error starts basically stops increasing or decreasing any further. So this is batch normalization, okay, done after seeing a batch. But there are a number of other normalization techniques as well. Of course, batch normalization is the most popular. The other one of them is called simply layer normalization. So this normalization is done after each example, not after seeing a batch. So let's say after each example, you have a value A, just one A, not 100 A's. And of course, A is a vector. And let's say I'm वही कहते हैं a vector of size 3. Let's say there are only 3 hidden units. So let's say 1, 0, or let's say 1. So it would normalize only this vector separately without looking at any other vector. And the usual approach is to use the kind of make this vector a unit length vector, meaning that you divide each value of this vector by the length of this vector. Okay, so length of the vector is what? Sometimes you can also write it as a L2 norm, okay, which of course is what? SQRT A. Let's say A is a vector at the A transpose inner product. So this is the L2 norm. This is also called the L2 norm. So you normalize that vector by the L2 norm. So basically what happens is जो ऊपर मैंने वेक्टर लिखा था, so the normalized A would then be, so basically 1 divided by whatever that normalizing factor is. Let me just write it as A, then 0, and then again, of course, 1 divided by whatever remains 0, divided by ठीक है. So इस तरह normalize कर देंगे. So this is called layer normalization, or in other words, normalizing each vector to be of unit length, or in other words, ensuring that each vector direction remains the same, but its magnitude is made unit of length 1. Okay. So in this case, we have normalized using the L2 norm. Sometimes L1 norm भी use होता है, but again, there is no upfront guidance which one would do better. I would just say, just go ahead and use the L2 norm. So that is another normalization approach. The third that I'm going to talk about is called group normalization. So this is similar to layer normalization, meaning that it's done for each vector A, but the normalization is now done for subsets of those vectors separately. मतलब, for example, जो A हमारा था 1, 0 और 1. course, this is a very small vector. What I would do is group these features or these outputs into a number of groups. Of course, this is very small. So maybe I can say my first group is the first two, 1 and 0, and the third is just 1, 2 groups. And now I will apply my layer normalization to each group separately, meaning that each group is a vector and each group vector is now normalized to unit length. Okay? So of course, if you want to normalize the first group, उसमें आपने 1 और 0 का लेंथ निकालनी है और उससे डिवाइड करना है. सेकंड ग्रुप की आपने निकालनी है तो 1 which is a scalar की लेंथ निकलेगी, उससे डिवाइड करना. So how do you select these groups? Usually there is no way, you just have to do it randomly. So random हम ये करते हैं typically. And by the way, अब ये random parameter क्या होगा, कितने groups बनाएंगे, all of these also becomes hyper parameters. So if you want to find the best set of hyperparameters, then these also becomes hyperparameter. How many groups should there be? What should be in a particular group? So all of these decisions are also in a way hyperparameters. And if you want to find the optimal set, you will have to validate, you have to evaluate over the validation set. So that was layer normalization. And now let's talk about overfitting in general and some of the approaches that are used in neural network to handle overfitting. So what is overfitting? So overfitting typically occurs if your model is complex and data is limited. Now, for a neural network, and of course, one way of quantifying the complexity of a model is the number of parameters. In a deep neural network, you have lots of parameters. Of course, some of the more modern neural networks in NLP that are currently developed, contain millions and millions of parameters. Actually, even close to 1 billion for example, GPT-3. Okay? So tons of parameters. So it means that such models are very powerful, very complex. And if you want to avoid overfitting, you will need lots and lots and lots of data. Otherwise, your network would overfit. And what does overfitting means? Your network has learned the data that you gave it exactly, including whatever noises and randomness were available in that data. It had learned it exactly. In other words, the training error has become very small. But when you run it on test set, it gives you high error because it has learned the noises as well for the data generating process. And it doesn't generalize to unseen examples very nicely. So this concept is called overfitting. And I think I mentioned this before as well when we talked about logistic regression. So the summary here is neural networks are highly to overfitting. Why? Because those models are very complex. They have tons of parameters, so they are likely to overfit. So how do you manage or control this? So we have a number of approaches. The first one is your standard regularization approaches. And essentially in the regularization approach, we basically change the loss function by adding a cost to that depends on the weight or that depends on the parameters. So this is same as we did for logistic regression. So basically the loss function by adding a regularizer term. ठीक है? And that regularizer term, of course, is based on, so the updated loss would be the original loss, which is based on error loss plus regularizer loss. And to control the interplay between the both of them, we have a scalar parameter lambda. And of course, this lambda now is again a hyperparameter. So the regularizer term is based on the parameters. So the regularizer term, let's say R, is based on, is a function of the parameters W's and B. And it usually increases with the increase in the absolute values of W and B. The most common parameters are the L2 norm or the L1 norm. Norm is basically absolute sum of all the parameter values. L2 norm is the squared sum of all the parameter values. And this term is added to the original loss function. And of course, the optimization technique would then try to reduce both, which essentially means that the parameters would tend to become smaller in values, absolute values. Okay? And as such, some parameters may be forced to be zero. Okay? So when, for example, let's say a particular parameter W, some W, let's say, is forced to be zero, which essentially means that a link between two edges, a link between two nodes in the network no longer exists, which essentially again means that you have deleted those two nodes, which means that you have made your model simpler. Okay? So this is an automatic way of ensuring that you can get a simpler model through an optimization process. So as I mentioned before, this regularization approach, of course, is also called parameter shrinkage, or sometimes we also call them weight decay, because the whole idea of this process is trying to reduce the absolute values of the parameters or the weights. Okay? So this is used in neural network. But in neural network, another approach has become recently very popular. And this approach became, I think, was proposed in the, I think, mid-2015, around 2015, primarily by Google, but by some other people as well. So this is called Dropout. So Dropout, this approach basically says that we randomly select some links or some weights in our network and assume that they are not there, meaning that we drop those links. So what essentially that means is that that link doesn't exist, so your network has become simpler. But we do this randomly rather than using an optimization process. So let me explain the process, and then maybe we will discuss some, you can say. So dropout is done for visible and hidden units, but not for output, again for obvious reasons. So input के लिए भी कर सकते हैं, hidden units के भी कर सकते हैं, but not for output. ठीक है? So let's say, and we have a probability P, ठीक है, by which we will drop a particular node. Let's say I'm talking about some hidden node, and let's say this point P is 0.5. So I will generate a random number, of course, generate a random number for each node and see if it is greater than, for example, 0.5, you select the node. If it's less than 0.5, you drop that node. And you do this for all nodes in a particular hidden layer. So if you drop a node, it means that that node and the links that follow it, the links that come to it, all of them have become redundant or zero, or do not play any role. So this forces your network to use the other links to learn the mapping from input to output. And as such, avoid the network to learn some, for example, noise in the data. So this is done randomly. And basically, this is done randomly over batches. So you're processing, let's say, 100 examples. For these 100 examples, a fixed set of nodes would be deleted in each layer, and that set is decided randomly. Then the next batch, you again do a random seed generation and select a next set of nodes to be deleted or removed or dropped. And then you do it again, and you do the training in this way. So in any particular batch, the number of nodes that are dropped might be different. And as such, the corresponding links would not be updated. Okay? So this forces the network to become, not learn the intricacies of the data and learn the general behaviors that are present through this randomness that is introduced in the training process. So usually hidden layers के लिए the dropout probability is around 0.5, or it could be lesser or higher. And again, this is a hyperparameter. So sometimes we also do dropout for the input layer. Input layer का dropout का मतलब क्या है कि आपके पास कोई भी input है, उसकी एक value आपने randomly zero कर दी, drop कर दी. Even though उसका original कुछ था उसमें, kind of noise add कर रहे हैं आप आपके input में. ठीक है? So usually input में we use a lower probability for dropout. ठीक है? Around 0.2. They could be different also, of course. So these are hyperparameters you can decide using a validation set. Now the question is, of course, if you have trained the model in this way by randomly dropping various nodes during the training process, it would certainly have some impact on the test set. Of course, to do this rigorously, you need to have maintained a log of what you have dropped, what you have not dropped in each batch of over the entire iteration set, which is actually not feasible. So what is typically done is that at test set, we simply reduce the values at each layer by the probability of that we have used for dropping that layer. For example, let's say if you talk about the input layer, P was 0.2, let's say. So now when you are doing a test set, and let's say आपके test set में कोई x है आपके पास, let's say इसके 1 है और 0 है, the test set that you now feed into it would be slightly modified, and that would be 0.2 into 1, 0.2 into 1, and of course 0, because 0.2 multiplied 0 remains 0. So this would be the test example that you actually feed into it. Of course, there isn't any very fixed theory behind this, and this is somewhat true for many neural network decisions. There isn't any hard and fast theory. Of course, there are intuitions, there are some theory, but there isn't any bounds and guarantees and stuff like that. But people have found this to work well, and they get good results. So two things here. What do? During training, we randomly drop some nodes. When I say we drop some nodes, we also drop the links that come into the node and go out the node. And this is done once for each batch in general. And as such, during that batch, those nodes and links are not updated. So after processing that batch, for the next batch, you do the random again and do it again, and you repeat and let the network converge. Once the network has been trained, meaning that all the parameters are fixed now, learned, use the full network without any dropping. But now you modify the inputs. If you are using, you have used dropout for the input, you will also modify the input. If you have used dropout for any hidden layer, you'll also modify the output of the hidden layer by a factor of the by a factor that's equal to the probability that you use to use for the dropout. So any questions here? So dropout, as I said, is now commonly used, and it can be used in combination with other techniques like the regularization approach, and layer normalization has some, the one that we talked about earlier, has some, you can say, generalization properties as well, but it's also more commonly recommended for convergence. Any questions so far? So as you can see, as we are adding more of these techniques, each of these techniques has their own parameters. These are then essentially hyperparameters for the entire model. So P here, for example, would be the hyperparameter. I think that there are a couple of other techniques, and I think I would probably go into that. I'll just mention one other idea, which is data augmentation. Again, we are discussing overfitting. So in the previous two techniques, regularization and dropout was trying to make the model simpler, was trying to introduce, for example, for the case of dropout, randomness, so that the model doesn't learn noise and random behavior in the training data. Okay? The flip side for overfitting is you need to increase your data. So that is data augmentation. But data augmentation is generally is domain dependent. Of course, data augmentation, by data augmentation, I mean that you have a data set and you want to increase that data set. But let's say if you can get as much data as possible, that would help your overfitting. Try to get as much data as possible. But let's say if you have a fixed amount of data and you want to use that data to generate more data, so that is called augmentation. Okay? So augmentation, as I said, is domain dependent, and it's most popular for computer vision and audio and video type of data sets, and less popular for NLP, although it is now becoming known in NLP as well. So let's say for images, what are some of the things that you can do to augment the data? For example, you can crop the data. Let's say if you have an image, you can do various cropping of the image and add that image into the training data set. So that is cropping, of course. You can, of course, do scaling. You can also do translation. You can also do rotation. So do these processings on the training examples and add them to the training set, kind of increasing your data with some randomness, some noise, some variations of the training data. Okay? So for image and video processing, these are some of the common techniques that are used for data augmentation. For NLP, one technique that is somewhat explored in recent years is to use embeddings. So embeddings, of course, are trained separately, and for each word you have an embedding. So let's say you have a word, let's say fish. Fish would have an embedding, and if fish occurs in a data set, you use the corresponding embedding for fish. But one way to generate new examples is maybe find embeddings that are close to using kind of similar to fish, for example. So using the embedding representation of fish, you try to find other words that are similar to fish, and then replace fish with those words. So for example, maybe you might find salmon, which is another kind of fish, as a, and its embedding is close to fish. Then you replace salmon, fish with salmon in a sentence and add that sentence in your data set. For example, मेरे पास sentence है, I like to eat fish. तो ये एक आपके पास एग्जाम्पल था, तो आप एक और एग्जाम्पल जनरेट कर सकते हैं, I like to eat ठीक है. So this is one way of maybe augmenting data in NLP. So in other NLP applications, there might be other ways. For example, my recent PhD graduate worked on the problem of paraphrase detection. So paraphrase detection means that you have a sentence S1, let's say, and S2. If there are paraphrases that, and of course we want to detect whether they are paraphrases or not, we will like, so given S1 and S2, we would like to tell, like the model tell us whether those are paraphrases or not. So paraphrase detection or classification problem. So paraphrase, of course, means that you have mentioned the same thing in the same way. Okay? So in paraphrase detection, you can also do augmentation by looking at the graph of relationship between paraphrases. So let's say S1 is a paraphrase of S2. And let's say later on, we also know that S2 is a paraphrase of S3. ठीक है? और ये दो examples आपके training data set में थे. From here, you can easily say that S1 is a paraphrase of S3. ठीक है? Because S1 is a paraphrase of S2 and S2 is a paraphrase of S3, which implies that S1 is a paraphrase of S3. So इस तरह की आप logic, and of course these logics are based on a graphical model of paraphrase and non-paraphrase, you can generate additional training examples with high degree of reliability. Okay, so I won't go into those details. You can look it up in the paper if you want. But I wanted to just tell you that data augmentation is quite relevant for neural networks and especially deep neural networks. And we would like to augment our data as much as possible. But these are usually domain dependent, application dependent, and you need to think of ways of extending or expanding your data set. So you can use word embedding, you can use the idea in this case of a graph and connectivity to generate additional examples, or for the cases of images, you can use basic steps like cropping and rotation to generate additional examples. Okay, so I think with that, I think I will conclude this. Any questions? Okay, now let's move on to the idea of attention mechanism. And then following that, we'll talk about the transformer. So when we were talking about the recurrent neural network or even GRU or LSTM, we had outputs at each time step, AT. Okay? So, and especially if your application is, let's say, like language modeling, if you're processing, if the output, if you have the output AT, which it means that this AT has seen the output xt, xt minus 1, xt minus 2 until the start of x1. Okay? And we also mentioned that theoretically, AT would have information from all of the previous inputs. But in practice, this information is often clouded because one reason is it might be clouded by some other words that appear in between the start and the end, or it might be clouded or might not be updated much because of the issue of vanishing gradient. Okay? So both issues are involved, although vanishing gradient is less relevant in the standard RNN, but it is relevant for GRU sometimes because GRU has many parameters and LSTM has many parameters. Okay? So, and of course, GRU, LSTM have cells and they try to move information forward. But sometimes that is not enough. We will need sometimes to add some other weighing factors to each input that we have seen so far and bring that weighted information forward. So this weighing factor is what is known as attention. How much attention do we want to give to a particular output? So let's say if I'm talking about A3, to compute A3, you must have seen X3, of course, then X2, X1. So you must have seen all of these. Okay? But let's say हमने कुछ specific attentions इनको डालनी है, कुछ weightage, extra weightage देनी है, maybe to X1 or maybe to X2. So we will need to compute those weights or estimate those weights as well. So those weights are essentially the attentions. And if we are able to attach an attention to each of those, let's say we call that alpha, some alpha, then I will say that alpha into X3, alpha, of course, each alpha would be different. I will discuss the notation in detail shortly. X2 and alpha into X1. So if you are able to do this, then you can give different weightages to different inputs that you have seen and bring those forward. So this is an additional way of controlling information in a sequence. So this is called an attention mechanism. So attention mechanisms can be used in standard RNN, in GRU, in LSTM as well. So usually what happens is after you have processed the entire sequence, you have another layer which we sometimes call an attention layer, और वो सारों की जो A's की output है उसके लिए एक alpha compute करता है, and then it proceeds forward. ठीक है? So this is called attention mechanism, and it can be applied to standard RNNs as well as variations. Okay? But we are not going to discuss this in detail, although it is used in practice. So we are going to also move one step further and say that in the standard RNN as well as GRU and as well as LSTM, information is processed sequentially. So no parallel So no parallelism is possible. So meaning that जब आपने कोई आपके पास कोई sentence है, I love the movie. So you first feed in I, then you feed in love, then you feed in the, and then you feed in movie. All this information cannot be processed all at once. ठीक है. So parallelism is not possible. So inherently RNN, LSTM, GRU are sequential in nature. So to address these two issues, of course attention का issue आप LSTM में भी डाल सकते हैं, but parallelism का issue हल नहीं हो सकता. So the model that is obtained by combining or resolving both of these issues is now what is known called as the transformer. The transformer is also a neural network architecture. ठीक है? So this is inherently parallel, just like a feed-forward neural network. All the information is fed in once, and all the information can be processed once. And since we have strong computational power over vectors and matrices through GPUs, this is much more computationally efficient. All of those can be done in parallel. Secondly, transformer maintains the sequential information and sequential importance through a attention mechanism, a self-attention mechanism. ठीक है? So two things हैं, एक तो inherently parallel and दूसरा sequential importance maintained through the attention mechanism. ठीक है? So this network is basically the transformer. So that is what we are going to look at next. So I think I will introduce the attention mechanism. Now we're also running out of time. Maybe we won't be able to complete it. So let's start with the attention mechanism in a transformer. And let's take the example of your standard language modeling, in which we, at any given point in time, we are only looking at the words that precede that point in time, including that word as well as the word that precede that word. We don't look at the words after it. ठीक है? Just like the standard recurrent neural network में एक word start से end तक जाता है, तो यहाँ भी we are talking about the same application, but of course we'll be feeding the information at once. So we will see how it works. Of course, transformers can be used for other applications as well, and we'll see those later on, in which maybe information from future can be used as well. But now we are saying that information from preceding context is only used. Okay. So to explain this first in a simple way and then the scaled version of it. So let me start with the simple version. So let's say हमारे पास so we want to get the output A3, let's say. By the way, to study transformers, I would recommend look at the section in chapter 9 of your textbook. Although it is not the greatest, but I think that is sufficient. और मैं भी उसी को primarily follow करूँगा. Slight notation difference होंगी because I want to make it consistent with the notation that I have been following previously. ठीक है? So let's say if you want to compute A3, which is the output after seeing X3, and once you have seen X3, it means that you have also seen X2 and X1. ठीक है? So the attention mechanism basically is motivated in this way that let's say you have X1, so you're talking about X3, right? So how can you quantify the importance of a particular vector with another vector? One way is taking the dot product or the inner product. So let's say if you want to find the importance of X3 with itself, you can take the inner product with X3. ठीक है? Similarly, X3 का आपने x2 के साथ इंपॉर्टेंस निकालनी है तो आप x2 के साथ डॉट प्रोडक्ट निकाल लें। x3 की इंपॉर्टेंस x1 के साथ निकालनी है तो x1 के साथ आप डॉट प्रोडक्ट निकाल लें। ठीक है, सो बोथ ऑल दीज थ्री वैल्यूज विल बी स्केलर्स। ठीक है ना, इंपॉर्टेंस ये बाय द वे डॉट प्रोडक्ट क्यों ले रहे हैं, बिकॉज सिमिलैरिटी है, राइट? डॉट प्रोडक्ट इज सिमिलैरिटी. You can use some other similarity as well, but this is the one that is most commonly used in practice. ठीक है, so if two vectors have a high dot product, large dot product means that they're more similar. So this is like a weighing score and attention, you can say. So now you have three values. Let's say we are processing x3. For x3 you have three values of attention: x3 with itself, x3 with x2, x3 with x1. ठीक है, so and you can call this scores, but we will normalize these scores to generate alpha. And now I use the notation. So we are talking about 3 because we are talking about the alpha for the output 3 at the time step 3. ठीक है, and then the previous जो थे वो मैं कह देता हूँ j. ठीक है, so इसकी notation ये है. So this is basically then so basically this is then the so dot product of x3 transpose into xj, and of course j is less than equal to I. This is a condition because we want to look at the previous. ठीक है, अब और इसके ऊपर एक्चुअली हमने सॉफ्ट मैक्स लगाया हुआ है. सो इन अदर वर्ड जो तीन वैल्यूज थी मेरे पास जो आई हैं मेरे पास, by taking the inner product x3 with x3, x3 with x2, x3 with x1, these are three values. This is like a vector. इस वेक्टर के ऊपर हमने सॉफ्ट मैक्स लगाया, which means that this vector is now normalized such that the maximum value, such that all the values will sum to 1. ठीक है, probabilities बन जाएंगी. So these probabilities then are our weighting scheme for this time point, which is 3, with all the previous inputs that we have seen, which is denoted by j, x3, x2, and x1. ठीक है, and then if you want to now compute our output at 3, we simply multiply this alpha 3j with xj, and of course this is sum. So you have a summation over j, and of course वो condition है j is less than equal to I. So my transformed, you can say, and weighted or attention based output at this point in time is given by the weighted sum of this previous three things. Weights क्या है, वो हमने वो scores या वो dot product से निकाले. ठीक है, so this is the basic idea. Of course इसमें learning कोई नहीं है, learning के लिए हमने फिर additional parameters डालने पड़ेंगे, but this is the basic idea of attention. कि अब at point x3 to get a3, we are taking the weighted output of the previous x1, x2, x3, and those weights are computed as alphas, which are scores, and they are computed as the dot product of each of those vectors. pairs of vectors. ठीक है? So in a transformer and in any other self-attention mechanism, we add additional parameters so that we can modify these scores more finely, and we can modify them through the training process. Okay? Just like if you remember when we talked about GRU and LSTM, उसमें हमने additional parameters डाले थे for the cell, for all those gates, for example. ठीक है? तो यहाँ भी हम parameters डाल रहे हैं so that they are adaptable according to the training data. So those parameters, we will call them, and I think probably ये थोड़ा सा time कम हो रहा है, थोड़ी मेरी tension हो रही है, आज ही मैं करूँ या next time करूँ, 136 हो रहा है. So we will have 3 set of parameters. So one is called the query parameter, Q. The other is called the key parameter. And then the third is called the value parameter. So we have now added 3 matrices as parameters. And the idea of these matrices is to modify those inputs, X1, X2, and X3 in 3 different ways. And those 3 different ways, we actually call them roles. And then we use those roles to compute our final attention output. मेरे ख्याल से I think I will probably stop here. So in the next class, we'll complete this. I think it will take about 15-20 more minutes. So that would be the end of the transformer model. The transformer has now become the mainstay in NLP and any other sequential processing task. And next class also we'll talk about the whole idea of transfer learning, the issue of fine tuning, the issue of pre-training. So we will also discuss that. And then what is left then would be, we'll be talking about machine translation and summarization in more detail in the remaining 2-3 lectures. And then if we have time still, then we'll talk about lexicon-based sentiment classification. Okay? So that is basically primarily the agenda for the rest of the semester. So any questions? So we will have a quiz, inshallah, on Monday, which would be your last quiz. And as I mentioned earlier on, this would include all material since the previous quiz. So about 2 weeks of material would be would be covered in this particular quiz. So also 2 quizzes would be dropped, N-2 policy in your final grade. And your last assignment should be out, or I think it's already out. So try to work on that as soon as possible. And you also have a project to work on. So there are a few things that you need to work on till the end of this semester. So please utilize your time efficiently.